So remember our goal of doing elementary number theory of in Lin. So I will slightly get out of my initial plans and leave the book of Island and Rosen for some time. Okay. So I don't know. So we have done an introduction. We have talked about unique factorization. So boop. I don't know how to go there. I'm going too fast. Okay. So I took a problem in geometry from the book of Island and Rosen, and we're going to solve it. So this is the problem. Let's suppose that we take several copies of a regular polygon, and we assemble it around a vertex. I tried to make a picture in TXZ, but didn't manage on time. So you take a polygon, and around the vertex, you want to put other copies, and you assume that it fits exactly. So you have exactly, m copies of an n polygon. And you want to prove that the only possibilities are 6 equilateral triangles, 4 squares, and 3 regular hexagons. Okay? You have the picture in mind? Cool. So, of course, I didn't even dare telling this to Lin in this form. So I just do some math on the paper to say, okay, I have this polygon, so the sum of inner angles is n minus 2 times pi because there are n vertices, and so the inner angle is 1 minus 2 divided by n times pi. And the condition that m copies fit is that m times this is 2 pi. So at the end, I get the equation mn is 2 times m plus n. And this is number theory. Okay, so we need to solve mn is 2 times m plus n in integers. And I don't know what you would do. What would you do?
I would factor it. M minus 2 times n minus 2 equals 4.
Good. Well, I did the same. And then you have to play with number theory again, saying, oh, okay, m minus 2 is an integer. It will divide 4. So roughly it has to be 1, 2, or 4. But maybe there are signs because now the subtractions. So probably it will be minus 1, minus 2, minus 4, or 1 to 4. And so this is what we get. And so we have a formula for m here. I'll try to get the pointer. It will be easier. We have a formula here, the form of f for n minus 2, and then n minus 2 is the opposite. And then you get 6 solutions. And you see that the only solutions that the problem was about are those ones. And those are solutions that do not make sense geometrically. Or maybe, but okay, so you can observe the symmetry in M and N. Here the equation is symmetric, so here we get the symmetry, those together, and this one is symmetric, and those go together. Okay, so now the goal is how to make a Lean program that solves the equation and gives you the correct answer. So here is the solution that Heather gave me after I showed her a long solution by myself, which did not fit the screen. Of course, the solutions that do not fit the screen are the best one, the one that make other mathematicians work for 300 years. But in this case, it wouldn't be appropriate. So, okay, so we have this stuff. So I don't want you to read it at once because I will, my goal this time is to explain every single line, is probably every single comma. Okay, so I will try to take the solution as well in another. I should put it here and hope, come on, doesn't want to go there. doesn't want to go there. So we'll have both at the same time. Okay. And I'll make it bigger so that you can read. Now it's processing the file. So here is the solution. So as you can see on the, is it big enough? No, probably not. Here we can try to make this bigger. Is it better? Can everybody read? Thomas, yeah. So so when we're here, we have, it's hard to see the bottom of the screen. But okay, so I'll just do it this way. Okay. So there is something that we start doing. Well, Heather starts doing in saying, okay, m and n, they are integers, and integers. An integer is a form of 0 or another integer plus 1. That's the definition we saw in the first lecture, I believe. It's natural numbers. Okay. I mean natural numbers. Later on, we talk about integers. So natural numbers, yeah, okay. So it's n here. Okay. Natural numbers starting at 0. So natural number is either 0 or no other natural numbers plus 1. And m is of this form, n is of this form. And so Heather is at once checking the first 4 cases where the first is 0, and she can test whether the first is 1 or whether the second is 0 or the second is 1. And then at this point, you see that we have 4 goals, because the first stuff with match this, comma, this, comma, this, it makes new goals. And we have 4 goals. And in each of these goals, we have the assumption that you see on the first line is m is 0 and the rest is still undetermined. And the second is m is 1, and third is n is 0 and n is 1. And so they match the tests which are here in the same order. And then the other trick, something called omega, that sometimes solves your problems. And here, she typed omega, and the machine says goals accomplished. You don't know what happened, but that's okay. It might sound bizarre, and it sounds bizarre for me because I like to understand why I have a proof of something. But so if I were young, if I were a first year university student, maybe I would want to compute and to say, okay, what's happening really? Here, I have no trace of what's happening, and neither do you. But of course, I know you can make the computation on your hand, and you can make the division by non-zero stuff when needed. And here the machine does it for us. So it's like a tool for advanced mathematicians. It's not a tool for first year people.
Well, what it's really doing is proving false from the hypothesis and ignoring the goal. Is that right?
I don't know what's it. Yeah. Sorry.
Sometimes it's using goal.
So in the one cases, it's doing what Alex said.
Yeah.
It's doing what Thomas said in the first and third cases, and what Alex said in the second.
Okay.
Yeah. What I really want to know is how Heather came up with this before we can come back.
Oh. No, omega is just in each of those cases, omega takes the assumption h and the goal and simplifies everything and goes on. Probably assume that the goal is false to get something that is easier to do. You know, when we are young, we often try to give proofs by contradiction because we have more hypotheses that you can arrange. This is maybe not so good from a point of view of constructive mathematics or stuff like that. It hates integers, so it's not a problem from the point of view of proof theory. And from the perspective of proof generation, it's a better stuff because then the algorithm has only needs to prove false. I mean, it's the same goal, whatever the problem is. Question is how to manage with your assumptions.
Lee's way of saying it's trivial to see that.
Well, it's not trivial to see that, but omega has been fed with many elementary formulas and so on. I mean, yeah, typing omega is some way of saying it's trivial, but sometimes you will mean that it's trivial. You type omega and you have nothing. And it's trivial, you know it. So
It is specific to the integer, the natural number.
maybe some other cases, no? No, okay. Okay, so now we have the non-trivial case. Yeah. Omega, there is no, I think there is no syntax here.
No, the syntax. Why match and end with?
Oh, okay. So I think she could have done mn to omega, but 0n to omega, and then 1n to omega. Now there is an error message, probably because, as you see, 0m was already matched before, so the machine complains. So we could have this. And
Matching. Have we discussed matching? I'll know what that match and with.
I'm not sure, I don't know. So here you have an example. So it's match something that is defined inductively in the system and matched by the possibilities. And I don't know. So I'd say that an integer is 0 or an integer plus 1. So when you say match, there are two cases at once. And then the second integer itself can be matched. And since the addition of n plus 1 plus 1, natural number, sorry. So let's, for me, integer is not, well, it's what it can. Okay, sorry. But I always say integer because in French, we don't say anti-natural numbers. We don't say number. In French, we say entier naturel, so integer, natural integer. And usually, well, I don't know.
So does maths check that like the cases you have are exhaustive, like will it throw an error?
Yep.
To try to delete the first case.
Yep. No, that one. So here was the error message. There are missing cases. Okay, so maybe I can't restore that. And what I didn't know before, Heather showed me that, is that you can match pairs at the same time, and probably triples. Okay, so now the last case is something is of the form u plus 2, v plus 2. And I typed u and v. She had typed m and n, but then my initial m was m plus 2 and n plus 2. It was a bit complicated. So m plus 2, u plus 2, v plus 2. And now you see what you have to prove at the end. You have an equation, u plus 2, v plus 2 is 2 times u plus 2 plus v plus 2. And you have to prove this.
We just figured out that because the first case was 0 or 1 for m, anything for n, or 0 and 1 for n and anything for n.
Yep.
Now it can accept anything plus 2 in either variable.
Yep.
And it knows that that's all the cases.
Yep.
Does it all automatically?
Probably if I type v here, I get something. Oh, no, it doesn't work. Okay, because then it would be v, but the machine wouldn't use that v is of the form v plus 2. And so then some further computation doesn't work. Okay, so we have this equation. And the first thing we do is to rewrite the right-hand side, h, which is u plus 2v plus 2. So if you expand the multiplication, you see that you get uv plus 2, u plus 2v plus 4, I think, yeah, is 2u plus 2v plus 8. And then you can cancel and you get 4 equals uv. In fact, mathematically, we get uv equals 4. So let's try to prove uv equals 4. And then there is a technique that works, which is called linearist, that we have seen sometimes, that basically takes the equation that we have, which is here, and possibly trivial equations like of the form u equals u or v equals v and 1 equals 1, and make combinations of this. And this combination has to be, well, it knows also how to cancel stuff, because it's not really a linear combination. We have also some cancellations to do, but then linearists prove the results. And for the end, it's for later on, it's simpler to have 4 equals u plus v. Okay. And so now, because 4 is u plus v, is u times v, we know that u divides v. And the answer is quite cryptic, is to vh. So one has to remind ourselves of what division means, what divisibility means. So divisibility, it's here, it means that there is some c such that b, so 4 equals u times c. And this is why it was a nice move to say 4 equals u times z rather than u times z equals 4, because then for c you can take v, and for the proof you can take h. Okay. Of course, we could have said by and then unfold probably dvd.dvd. Yep, well, it's not so this simp, maybe. No. Well, let's try. And then unfold nat.inst dvd. Yeah. Sorry, and this simp. Okay. So behind the scene, it means that there is this C, and now it exists something. So it's still on the blackboard over there on the right. You know that you can type use. So if I were a first year students, so there must exist C. So use C, but there is no C. So okay, use V, and then machine says it's finished because it had to prove that 4 equals u times v, and it's already there in the stuff which is over there, and so the machine. Okay, and now I could type linearist. Okay, another way to do the proof. So certainly Heather wouldn't have typed this, and I wouldn't have, because I know that when I want to prove divisibility, I enter use with the factor. So I would probably have typed this. And then with this proof, I know that I would have done really something else, which I'm going to show you what I want to do when I'm here and I don't have the skills. So now I take this expression in H, and I say, okay, I want to make the u plus v plus the uv on the p and the u plus 2. So I need to say that it's a multiplication times an addition, distributivity, and addition times multiplication. So I would use mul add. So at H, and then you see that it has expanded the multiplication. And then I need also to use add mul for the left. So now I have uv plus 2v plus u plus 2. And so now what do I want to do? Probably to put the 2 on the right here in front of the u plus 2, because it would help me. So multiplication is commutative, and the second argument would be 2. If I say multiplication commutative, it will work on the u times v, which has been changed to v times u, which is not what I want. So then I want specifically to take the u plus 2, v plus 2 stuff. So I say will come something with 2, and it's on the correct size. Now on the right-hand side, I want to say that 2 times blah, blah, blah. So same will add. What happened? Oh my God. So, okay. So mul add, not mul add 2 won't be enough, but okay. So mul add probably 2, and then something of the form this way, so that it's forced to work on the right-hand side. And maybe I want to put the 2 times u plus 2 on the to exchange the order of addition on the right. So okay, now I won't try to write 2 times u plus 2 in full. So I say, okay, work on the right-hand side. And now use commutativity on addition of the right-hand side. Doesn't work? Is exactly what I'm trying to do, but what? Yeah, I'll show it, but I want to show the. Oh, so it's at h. Okay. No? Yes.
Really converge as at h.
Yeah. Okay. So it worked. No, it didn't. Yes, maybe. Yeah, it did. So what happened between the first line and the next one is you see on the right, on the right-hand side, the addition, the order of addition has been switched. Okay? And so conv right-hand side means do the following operations on the right-hand side of the indicated equation here, which is h. So the right-hand side. So yeah.
Yeah. I don't want to change it. Let's say first, not the second, or maybe third. Instead of right.
Yeah, okay. So I could also have done that. Okay. So this works. And I could also have said, okay, I want to play with some instance of addition. So we have to guess which instance of additions is that one. So probably the third one. It's not the 1, 2, 3, 4, 5. It's not the fifth one because logical arithmetic expressions are trees. And what the machine is doing is navigating on the tree. So it's probably the first one should be this one. The second one was probably that one. And here we have the third one. So I typed n3 right, 3, and at com at h. And it didn't work. It didn't work. It was not the third one because the third one was that one. So then, okay, I tried to be clever once, but only once. And four was okay. Okay. And now I have it. So now probably the machine could try to cancel by itself at h. And it did. So same question mark. And sorry. And you see you have this simply not at right cancel here. So I do that and simplified. And now what do I need to do is probably at com v2 h and also mul add at h, and now probably the same stuff should work. And now I have this, which is not exactly what I want, but probably sympathetic would get it. And now I'm done. Okay. So this is really what I had done myself 3 days ago. But we have followed classes by Heather, and now we know that. Sorry?
Did you want to put sim at the very end? Because it's
Yeah.
running linear.
Okay, so that's another proof, but we'll keep this one. Okay. No, it was the. Okay.
Probably don't need H line by linear.
Yeah, but we had H already, so. Okay. So this angle bracket syntax it's complicated, but basically, when you enter brackets, you are really entering what mathematicians will call a tuple, or which people call a sigma type, and it means that division is there exists something such that something else, and so it's a pair of two stuff. And the bracket allows you to enter the first argument, comma, the second argument. So the first one would be V, and the second is a proof. Okay. It's order, yeah. Of course, if we can try, but what happens if we put?
So this is again like a witness and a proof, right? Like
Exactly. So if we put HV, the answer is H. The argument H has type 4 equals U times V. It's expected to have type N.
So like, does Lean know that like for a division statement, what it should, like, the witness should be getting the other factor? Is that what's happening here? Yeah, that's how it's defined. Or yeah, but like in this case, it's the V such that it's V equals 45 to H.
I'm sure I understood your question.
Like, what is like if this were a chain, I would expect it to be like, you know, witness column or like
Yeah.
Like the angle bracket. And here I'm asking if like the role that the V and the H play is the same as in that case, where like is
exactly. That's why I had showed you so VH. When we unfold not DVD.dvd and unfold not.inst dvd and the simp, sorry for this, we'll see that really what the division symbols mean that there exists C, and the C is where the C is a type NAT and proof is. So it was really that. Of course, it's not really visible, but since it's only a matter of rewriting the definitions, Lean does that. There's something called beta reduction, I think it is that, and proving something by equalities by beta reduction is an algorithm. So Lean always tries to reduce and test on the reduced forms.
Thank you very much.
Yep. So okay, if I use V, it's done, because then the machine says, okay, it remains to prove that H, and H is there. So it's another way to do the proof. I could type.
Exists I, all one word. Like exists I V. And that doesn't, that's literally.
Okay, okay, so that's a short name to fill and then to fill the rest. Okay. So all these tactics, for example, this one, I never knew of its existence. Yeah, they're made to make things clearer at some part of your own development in Lean, and of course, and I for introduce. Probably. Okay, so we have many ways to prove that, but let's keep one that works. Use V for the moment, and okay. So now back to our story. So now we know that U divides 4, and we want to know that U is smaller than 4. Okay, so there's something called NAT LE of DVD. Let's say that if you have a natural numbers that divide something, it's smaller than something, except that when you are dividing 0, you're not smaller than 0, because 42 divides 0. Okay, so when I apply NAT LE of DVD, I could say this, because just I apply this, and I get to prove two things on the right-hand side: that 0 is strictly smaller than 4, and that U divides 4. And of course, U divides 4 is already proven. It was this. And then there's question mark underscore that says there's something to prove, I know, but let me do it afterwards. And afterwards, we have to prove 0 smaller than 4. And then there is this other tactic called norm-num that says reduce natural numbers to whatever they can be and check because it's on hands. And so 0 smaller, strictly smaller means that you can add a non-zero number to 0 to get 4, and well, it's done. Just counting bars in the definition. So norm-num does the job. And
Do it by use for. Chronological because use for solves it to have a strict.
no, but he made a use.
That's short. Yeah, it's circular. Yeah.
It's circular. So, but use for didn't work. So
If it was 1 is less than 5.
oh well,
You would be left with 0.
I don't know. In this case, I don't know. And in some cases, you have. So I could show you that. If you have. Sometimes you have to prove 0 smaller than 2. So you could do by norm-num. Okay, that works. But you could also do exact nat.0 le2. Oh, no, that doesn't exist. So let's try 0 le1. Doesn't work neither. Maybe it's too, well, okay. For example, for 0 strictly smaller than 2, there is nat.2 strictly positive, but probably norm-num we do it as well. Well, just a matter of what you type. It's cool. I like nat2 post when I have to fill this proof to another formula rather than typing by norm-num in the proof, but okay. Okay, so now we have u is smaller than 4, and then there is this other tactic, interval cases, that say, okay, you know that u is smaller than 4, so it must be 0, 1, 2, 3, or 4. And then in each of those cases, apply omega. And so I will just remove the end of the line. If I have removed the end of the line, I have 5 cases, 5 goals, which correspond to u is 0, with u is 1, u is 2, u is 3, u is 4. And in each of those cases, the proof, the omega tactic would work. And then I have to type this. And if I type it once more, I have one. So I have this 5 omega, and there is a syntactic way of saying do the same stuff in each cases, which is bracket semicolon. It's not a semicolon, it's a inferior superior. And then you have omega. Okay, so that's Hazel's proof. So now.
Nuclear interval cases takes a proof that a natural number is less than something.
Yeah.
And makes that many goals with each possible value.
Exactly, and possibly if you feel several inequalities, it will accommodate with those inequalities. But those inequalities have to be something is greater than something or something is smaller than. So you have an example that if n is at least 3 and strictly smaller than 5, then it's 3 or 4, and interval cases n, all goals same. So all goals something is the same as inferior semicolon superior, that stuff. Okay. Okay. So now let's do the same equation in integers. So there is a tactic missing in Lean for the moment, but maybe I could have done it. So the first thing I did is to solve the equation for myself, because I need to feel the statement of the exercise. Okay. But so I have found the other solutions, and we had seen them on the blackboard anyway. And I start really in the same way by n minus 2 times n minus 2 is 4. There are various options here to prove the result, and I want to show you one. So I won't show you by computing because I did it already. But here we could say also h m minus 2. It's 4, sorry, I'm typing that. And applying the tactic. What? So I wanted to type the tactic ring, but it's not clear because it has to use the goal. So to make ring work, I think I have to rewrite a little bit of mul add and add mul. Now I have m times n in the goal, so I can plug the equations. What's happening? It's not add mul because it's a subtraction, so it's mul sub and sub mul.
Ring doesn't see the goal, but literate does.
So the opposite. Ring only sees the goal.
Sorry, it doesn't see the hypothesis.
Yeah. But now when I've done that, I've replaced the m times n by its value, and now it's always true. So now ring would work. And that proof wouldn't work for integers, for natural numbers, because natural numbers subtraction is a bit complicated. If you are in elementary school, it's not always defined. In Mathlib, it's always defined, but it's truncated to 0 when it should be negative. And so it's not always true that a minus b, or maybe it is. Maybe it's true, but it might not be true that I think it is. No, but a minus b times c is a times c minus b times c. I think it works. So even with truncation. So, but you see, there are algebraic formulas that don't hold for natural numbers, and so sometimes it's complicated to prove something with natural numbers. Okay, but that's another option. And bizarrely, there is also the linear combination that should work, but it doesn't, because you have to tell a linear combination that it's minus the equation h rather than plus the equation h. Nope. It's with. Yeah, it's h, sorry. And omega doesn't work neither, because you need to fill in the hypothesis, I believe. Oh, no,
If you type, if you ring normalize by taking ring and
so
f,
omega, yeah, omega works, sorry. Okay.
but it works because you already have established it.
Okay, omega doesn't work. And you say that if we type ring and f, no, put it in a norm. Oh, it worked. Okay. So it requires some skill to be used to using those tactics to find the cases. But it's good to know that they exist and to try them. Okay. So okay, and now we need a bit of work. So there is something that says that if you divide a power of a prime, then you're not exactly a power of a prime, but you're a power of a prime up to a unit, which is called being associated. And so I apply this, and I get the stuff. So I got it. So I said that m minus 2 is associated to some power 2 to the I of 2. Because Lin knows that 2 is a prime as an integer, not only as a natural number. Then I rewrote that what it means to be associated. And for the integers, it means that you're either plus or minus the stuff. And so now I built the same tactic as I did, interval cases and I. And in each case, I played the OR case. I split the OR case, either m minus 2 is plus the stuff or minus the other stuff in two cases. And I simplified in the equation and applied omega, and it clears the goal for me. Otherwise, there would be 5 goals for you and 2 goals each time, so 10 goals with this identical proofs essentially each time. Okay. Excuse me?
What does the width keyword do in general? Like,
What is the?
the width?
Our case is with.
Our case with is you take this HU, which is A or B, and you call something for the. So I could have written this. HU is or is something is a minus 2 is something, or my a minus 2 is minus something. So I could have said HU plus HU neg. But then the problem is that now I can't. It's sometimes HU plus that I need to fill in, and sometimes HU neg. But in each case, in every 2 cases, one of them doesn't work. So I'm used when I split the OR condition into 2 to calling them in the same way. Sorry.
Earlier we used the math statement for this, right? Here we're using our cases. So here it looks like it's automatically detecting, like.
So
I guess, like, how does it know that the sign is the thing that it's casing on?
no, the cases the R cases split. So I should not do interval cases. For example, let's say R cases HU. So HU, you see, it's sorry. HU is over there. It's a NOR condition. So if I want to use a NOR condition, there are 2 cases. Either is the first one. Okay. So R cases it splits with HU plus and HU neg, and the syntax is this pipe between the 2 stuff. And now you see that at this point, sorry, here it's not a space. Okay, I have 2 goals. No? Where are the goals? Yeah, I have 2 goals. One where m minus 2 is 2 to the I, and the other is minus 2 is minus 2 to the I. Okay. When you use this inferior semicolon superior stuff, it's really it's always the time that you will be confused as sorting out what's happening, because the same code is applying in every cases, so the error messages can come from all over the place. So, but when it works, it's cool. And usually what I did is really having 10 proofs and then squeezing them into this stuff. Not exactly 10, but of course you did.
The first little h, can you reduce to your previous 0?
Not really, because, well, I could, but
There's no tactic that if you have in the integers the product of 2 things before, then
yeah, but then you need to know that m minus 2 is not the same m minus 2 as it would be if m is smaller than 0. So there is a tactic that says if you want to prove something in natural number, you can try to prove it in integers called zify. And I'm not saying there is natify.
There's lift, but it only works if you have a hypothesis that there's no lift.
Yeah.
And we don't. These could be negative.
And m minus 2 could be negative. So
if you have p times q equals 4,
yeah,
in the integers, there's nothing that says therefore, there exists natural numbers a and b, so that a times b equals 4 and a equals p and b equals q, or a equals negative p.
well, there is something that says that the absolute value of p times the absolute value of 4 is 4, because it's called nat abs. So you would have that the product of absolute values is 4. Then you could try to do something using the first proof, and then you would have to say, okay, now p is either the absolute value or minus the absolute value, and you'd got 4 cases. 2 of them would not work. When you put
just 2 cases, you should also know that the sign.
well, maybe the function exists, maybe it doesn't. I don't know. I mean, Mathlib had reached the state where it's almost impossible to guess whether something, well, to find out whether something exists. Okay. So I want to go back to this. So something I've explained to you already. And now I want to do some formatology. Because it's impossible when you're a Frenchman to talk about Diophantine equations without talking about Fermat. So, I mean, I have 10 minutes, so maybe I'll show you Lean proofs, maybe I won't. Maybe I'll just show math, sorry, showing what one can do in Lean. And if I want to show you Lean, I'll show you the second one. So the first one is a nice cubic equation due to Fermat. A very easy one compared to the one of Fermat's last theorem. But that's it. So you take x cubed plus 2z cubed equals 4z cubed. And according to Fermat, it only has the 0, 0, 0 for solution. Okay. You've proved the generalized Fermat equation. Okay, so the proof is by descent, something that Fermat essentially invented. And so the idea is you take a non-zero solution triple and you build another one, which is smaller in some sense. And if you could go on once more, you'd get always decreasing the sequence of solutions, and it's impossible, it cannot happen. Okay, it's not possible for integers, for natural numbers. Okay, so how can we work on these equations? The point is that x cubed is obviously an even number because 2y cubed is even and 4z cubed is even. So we can write x is 2 times u. And then I should have put pause, but then if x is 2 times u, the equation becomes that 4u cubed plus y cubed is 2z cubed, from which you see that y is even as well. And so you write it 2v, and then you rewrite the equation, and now you have z cubed is equals 2 times something. So z is even. So z is 2w. And then when you divide everything by 2, you get u cubed plus 2v cubed plus 4v cubed is 0. And so the triple, well, you've divided everything by 2 is still a solution. And in some sense, unless the solution is 0, it's smaller. So by infinite descent, you have a contradiction. Okay?
Is there some speed?
Sorry?
You've got v cubed plus.
Here it's an equal sign, sorry. Here it's this plus this equals that.
And is it w?
It's w, yeah. I didn't. Okay. Well. Excuse me? I said an equation is even? No. So, yeah, wow. No. I'm okay, no, expression is lousy, sorry. So I mean that x cubed is equal to that, means x cubed is even. And so x is even. Okay? So I'll correct the typo. There's something I want to show you on that proof, but I'll show you on the other one because I don't want to show you the solutions. What's happening? So here is a proof. So I had written for you a lemma that says that if a cube is even if and only if the number is even because, okay. So now I prove that x is even. Oh, sorry, it's processing. And suggest that you could do the proof, but it's not so. But I suggest you have a look at this function, not even add. And then if x is even, then u is x is u plus u. That's the definition of being even. And now I can prove that the second equation, and from that equation, I can prove that y is even. I rewrite y as 2 times v, well, v plus v. Then I have the third equation, and then z is even. And at the end, I have the equation k, which is u cubed plus 2v cubed plus v cubed is 4v cubed. Okay. Now I want to show you the rest of the proof. So there are two cases. I had to decide how will I do the descent stuff. So I have three numbers. It's hard to say that the three number, what's the measure of the size of the three numbers. I took the sum of the natural numbers. It worked perfectly. I was not sure it would, but it worked perfectly. So I say, okay, there are two cases according to which x plus y plus z is 0 or strictly positive. And so the first case is, I'm here. So you see with h, so I have the small assumption h, x plus y plus z is 0. And in the other case, I have the assumption x plus y plus z is strictly positive. Okay? And so in the first case, the machine is, yeah. Well, wait a minute. You're too fast. So in the first case, I say, okay, in fact, you can simplify h, and the machine will tell you essentially that x is 0 and y is 0 and z is 0. Not exactly in the form required, funnily enough. But, and in the other case, what I said, okay, apply my theorem to the triple UVW. And so now I have applied my theorem to UVW. And once I know that u is 0, then it's easy to find that x is 0. And what the machine does by itself is understanding that something has decreased in the process, because u plus v plus w is strictly smaller than x plus y plus z because it's positive and blah, blah. So the machine proved just behind the scene that I could, the theorem was by induction, very strong induction, already proved for the smaller values, which is not really an induction on naturals. It's not stated as an induction on n plus x plus y plus z, which we could do on paper. It's really an induction on the triples of three integers, and something decreases, which is the sum of the elements. That shows that it's well-founded and there is no descent. At the end of the compilation of the theorem, at some point, Lin says, okay, you want to apply recursively. So if there is something I cannot prove, it will leave me with a proof, something to prove. That guarantees that the computation will decrease. Yeah, but here the well-founded property was found automatically. It's totally miraculous. Okay.
And if you don't do that case, which does it make?
Ah, yeah, good idea. So I will solve so let's do that. So I move this. So now I have applied my theorem to UVW. That's okay. So recursively, so now I say, okay, I will do the proof. So x is 2 times u, so I will rewrite HU, HV, and HW. Sorry?
Maybe we can only test this with all the sort. Maybe it
and I have no goal, and what happens? And now there's something is written over there, which is not the same error message as before. It was not the proof as stories. It's failed termination, failed to show termination for Fermat with errors. He couldn't understand that something is, okay? And I know that there is some set option, blah, 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 that will tell you how Lin proved the termination, but I don't know the code, so I can't show you how it did. But, I should have done that, so now I will do that, and okay. And yet another equation, still different, but with another reference to Fermat. So So it's taken from a Putnam competition. You take the solutions in natural integers of the equation 2m is 1 plus n times n. So m divides 2m minus 1. And you have to prove that either m is 0 or m and n are both equal to 1. This one is, I found it more difficult, but mathematically. But so I want to show you the first steps. And the lean code has the first steps as indication. So I will. I'm not doing a strong induction proof here as in textbook. I will just take the smallest prime factor of m if m is at least 2. If m is 0, yeah, you observe that you can take n anything. If m is 1, you get that n is 1. But otherwise, we have to exclude the possibility that m is at least 2. So I take the smallest prime factor of m. And 2 to the m is even. So mn has to be odd. That means that both m and n are odd, and p cannot be 2. So 2 is a non-zero element in Z but P. And so it has finite order dividing P minus 1. Okay. We have Fermat's little theorem, say 2 to the P minus 1 is 1. Well, 2 to the P is 2, and we can divide by 2. So 2 to the minus P is 1. That means that the order of 2 divides P minus 1. And then one has to prove that the order of 2 is not equal to 1. That would mean that 2 is 1 mod P, but that means that's impossible. It means 1 is 0 mod P. And, okay. And also, one has to prove that the order of 2 divides the integer m. And this is because when we reduce this equation mod P, you get 2 to the m is 1. And by definition of the order of an element of group, m has to be a multiple of the order. So we have these three. I hope I'm really writing on my sorry, that's okay. So I can't erase that. No. Oh yeah, it's not. What's happening? And so now we need to get a contradiction. So mathematically, the contradiction is easy. In Lean, it's not so easy. So R divides P minus 1. It divides M. So it has to be smaller than. Okay, you know that P is the smallest prime number of M. So if I have a non-trivial divisor of M, it has to be a multiple of P. It has to be, sorry, it has to be bigger than the smallest prime factor of M, so bigger than P. So from this, I get that R is at least P, or it's 1, but it's not 1. And so I get the contradiction. And so you can do that in Lean. And I was fortunate to observe that this morning that my proof at 8 o'clock was even more complicated. So here, we have to prove the statement. And I've given it as an if and only if. So we have to prove that solutions are of this form and that the stuff of this form are solutions. So if I do a constructor, I get the two cases. And the difficult case is the first one, and the verification is the last one, but I want to do the verification first so that it's not lost at the end of the file. So swap says that when you have two goals, you just exchange the order of the goals you're going to prove. So once I've done swap, you see that the goals are swapped. And their names, MP and MPR. MP is when you have an in and if, it's an implication, mod imponents, and the other implications is mod imponents reverse. And so the names are there, but the names do not change. So here one has to prove that this gives solutions, and here one has to prove that to solve the equation. So now, again, there are two trivial cases, m is 0, m is 1, which I check out by match, and I let you guess what you can do to finish the proof. And here again, if m is 1, and now for the serious part of the equation. So we want to prove that it cannot happen. We want to get a contradiction. So we apply the tactic el falso that says that it suffices to prove false to prove anything. So el falso. So now I have a mess of m plus 2 all over the place, and it's complicated to read. So I just said, okay, write capital M for m plus 2. And ideally, I would have typed capital M here, but I'd lost the hypothesis that capital M is at least 2.
I think you can write capital M parentheses n plus 2. Like M with the
at.
email at. All no spaces. Not so never mind.
No, but
Sorry.
at least when one needs something. So just to because it's easier to solve. And also when I apply simp and I have m plus 2, I don't want that m plus 2 is taken back to m for some reason. So okay. So now I take the minimal prime factor. So again, in Lin, all functions are total. So when you ask for the minimal prime factor of any number, it gives you a solution. It gives you something. If you ask for the minimal prime number of 1, the function gives you something. And it cannot give you a prime number, so it gives you 0 in that case. When I said ex falso, I obtained that instead of proving this, which is what I want, it's sufficient to prove false, because the false implies everything. I need to prove that m plus 2 is 0 or m plus 2 is 1. But here it's, it's impossible that this happens. So I won't prove that. I will prove false. I will prove that I have a contradiction for all my assumptions. And a contradiction implies everything. And ex falso is that. It changes to goals, asks you to prove false, and then it's enough. Which it's sometimes useful when you want to prove something by contradiction, and you have to some cases split, and the impossible cases, you prove them using ex falso. It comes from Latin. It said ex falso quod libet. Everything comes out of false.
If you left that line out, would it still work?
Oh, no, not at all. But it will work. For the moment, I don't work on the goal, but at the end of the proof, yeah, it would work. What happened? No, here, okay, here it works. Here I said apply something, which is applying inequality, and inequality does not, okay?
Actually never returns 0, because it always returns a divisor. So if 1 it returns 1, and the 0 returns 2.
Okay, it returns, okay, it was a choice, okay. So 0 is this, okay, so, okay, you're right. So 2 is a divisor of 0. It's the smallest prime number that divides 0. So it's just for 1 that it returns 1, which is not a prime. Okay, so here you see, you're right. So now here I want to prove that the p that I got is prime. And so there is a function nat min fac prime that says that minimum factor is prime. And when I do it, I have to prove that m is different from 1, which is a stunt. And I don't want to prove it. So here I was inspired by Heather's lessons, and I typed linearis, and it worked and gone. Okay, and this is I give you on the sheet because I don't want you to guess that. So now we have to prove that the order of p divides m plus 2, and then there is this function nat min fac dvd. That's always true. That's cool. And now this stuff about the order of 2 modulo p. So I have just defined R to be the order of 2 modulo P. I want to prove that R divides M. And what does it mean that the order of something divides something else? Is that the thing to the power stuff is 1. So there is this function, order of dvd, if and only if power equals 1. And now I have to prove that 2 equals m, 2 to the m is 1. But it's not the same 2 as, it's not an integer now. You see, it's an element of z mod p. And here it's a 1 of z mod p. And then I need to prove that r divides p minus 1. So there is a general function that said, okay, assume that, and here I have to prove 2 different from 0, but it's the 2 of z mod p and not the 2 of z. Okay, so r is non-zero, r is not 1, r is strictly smaller than p. It's a messy proof. Maybe Heather would do better than me, but it's only what I could do. And now I get that it's not true that p is smaller than r. And so I apply this inequality, this stuff. So I want to prove that p is smaller than r, given what is there. And you know, p is the smallest prime factor that divides m. So it has to be a greater, it has to be smaller than any divisor of m. And I know that that r is a divisor of m. So there is this function nat elim in fact prime that does the job. And I only knew about nat elim in fact, which works about with prime numbers. It's a mess, so this is good. And so now I have to prove 2 things, that either m is 1 or p is smaller than the minimum prime factor, which is true because it's equal, and m is 1 is not true. That's okay, the secondist. And I have to prove that 2 is smaller than r, which is true because I have proved that r is non-1, and also r is not 0 because the order of 2 in z mod p, what could it be? Z mod p is not a group. It's multiplication, because order of is for the monoid structure of multiplication. So if you take an element of z mod p, 2 things can happen. Either some power is 1, and the order will be the strictly strictly positive integer that makes the power being 1. Otherwise, no power is 1, like if it takes the order of 0 mod p, and then the convention is to return 0. At least, and so I have to prove that 2 to some power is 1, and this is true because it's Fermat's little theorem in some sense. But one has, you have to prove that that r is at least 2, and you get it. Okay, so there's still work to do if you want to fill the proof, but I think I should stop here. Thank you. Any questions anymore? Maybe we need a break, everybody. Okay. It's like in the, there is a train movie with, oh, what's the name of the guys? They say break, 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 and they crush the machine.